Hi, welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and I'm with.
Robert Moore, nice to meet everyone again.
Hey, Robert, do you realize this is episode number 18?
18. Seems like just yesterday. No, it was a lot colder yesterday.
Well, we started these, I think it was January.
January, yeah.
Yeah.
So it was much cooler than it is right now.
For sure.
So,
in this podcast, we talk about all things related to physics, astronomy, astrophysics, science in general, and it gives us a way of communicating to the public things that we find interesting ourselves, maybe things that are making the news lately, or different topics that kind of takes people's interest, that they want to know more details about. And of course, we do have a live chat. So.
I was about to say, that's why we invite questions on the live chat and actually comments on YouTube when we post this. You know, we're not chasing the follows, folks. We're wanting to share our information with you.
Exactly. And we're broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
Now, when you hear North Dakota, people think, oh, that must be where snow comes from, right? That's where Santa lives.
It's supposed to be 90 degrees today, folks.
Yeah, it's extremely warm. In fact, we kind of seemed like we went from winter right into summer.
We did this year.
There was like almost no transition, no spring. So, but anyways, the other thing is, if you're interested in science, if you're interested in arts, if you're interested in any higher educational type of programs, please consider coming to the University of North Dakota. We have a lot of wonderful programs. And the other thing, too, in recent times, is you do not need to physically be here, Robert.
I know.
In fact, if you lived in New Zealand, you could take courses at the University of North Dakota and never leave your home country.
I would prefer that you drop by the office, though. I would prefer that you had to come here. But, that's me. I in this capacity at least, I like meeting with people and talking with them. So.
Well, that's one of the advantages, of course, of being able to take classes online, is that as long as you had an internet connection, you can essentially be anywhere in the world and beyond. So you imagine in the future, right, people will be taking online courses, and those people will not be on Earth. They'll be living in a base on the moon.
That would be nice.
Or they'll be living on Mars.
That would be a 20-minute delay at best.
So you can imagine, there's all kinds of flexibility in technology, yes. And as things progress into the future, the imagination, is the only thing that stops you from thinking about what is the different types of situations that will arise in the future.
Right.
Hopefully all for the betterment of humankind. The fingers are crossed.
That's the plan.
We mentioned, of course, that we're into summer and the temperatures are warm outside. And, in the summertime, one of the things you kind of focus on, and you notice more of it than you would in the middle of the winter, is the sun.
The sun.
And so today, a lot of our discussion is going to be based on
the sun.
The sun.
Our nearest star. And a lot of people just seem to forget that. The sun is a star. And, funny story here. At least I always thought it was funny. In my graduate work, I was once discussing looking at stars with one of the professors. And I brought up the point because, he was kind of decrying my interest in planets and planet formation. And I was like, I get where you're coming from. But, even so, if I wanted to look at stars, and he just kind of grinned and goes, "You've got a point." And I was like, "Thank you." Got a big one real close, relatively speaking, right there in the sky. So.
Well, that's the benefit, of course, of the sun being so close in terms of distance.
Right.
That there is a lot of things that we can study in detail of our own sun and then see if that, is common in other stars as well.
Absolutely.
Try to make that connection. Or you can even go the other way. You might determine some property or characteristic of stars and then see if our sun has those sort of characteristics.
Absolutely.
In fact, I always, mention in my intro astronomy class that one of the connections you make as a young child is when you realize that the sun that you see in the sky in the daytime is actually a star like you see, very similar to what you see at night. The difference being the distance.
Right.
So if you can imagine, do this thought experiment where you take our sun and you move it magically away from us. If you keep moving it further and further and further away, it becomes so faint that eventually it is like one among all the other numerous stars that you see in the nighttime sky.
That will actually be one of the problems when we become spacefaring, is how do you find your way home? The sun just looks like any other star.
Yeah, so I mean, there are ways. Well, it's when you bring that up, it's interesting. We've sent out some probes, as you know, like Voyager 1 and 2 and others as well, into the outer solar system. And these probes have reached a great enough speed that the sun's gravity is not strong enough to bring those objects back to the inner solar system. So these objects are going to continue to move away from the sun forever. In fact, they're going into orbit around the center of the Milky Way.
Right.
So where would these objects be, let's say, 100 million years from now? So they're not going to be in the vicinity of the sun, clearly. And so if some creature, some life form found these objects, how would they be able to determine where ultimately they came from? What is the origin of these spacecraft themselves? Right. Okay.
I don't know.
So let me double check that. So it's okay. So so we thought we had a technical issue here, but we don't. So if some life form found these objects, let's say the Voyager 2 spacecraft,
right?
What method, what technique do they have to determine where it ultimately came from? Because it's been in orbit around the Milky Way, let's say, for roughly 100 million years, far away from our sun.
Right.
So there's no easy way to pinpoint its origin.
Even with what we did with the gold record, it would still
That's what I'm getting to.
Yeah, it would still be difficult with what we did on there, which was, for those of you who don't know, we put the pulsation rate of several known pulsars and put information about our distance from each of those. And the bottom line is we used 7 of them.
It was something in that order, yeah.
Yeah. With 7 points in space in general, 3D space, you can pinpoint a location. But those guys will have moved in 100 million years. So will we still be at the crossroads that we're showing on that disk? But it's a lot better shot than trying to describe it in terms of constellations you see and the things like that.
Well, that's it. I mean, you can map out from Earth, of course, the location of the various stars. You can keep track of their motion through space, because remember, the stars are not stationary, and I don't mean the movement of stars throughout the course of a night. That's due to the Earth's rotation.
Right.
Right, from west towards the east. So stars look like they're going from east towards the west. But stars have to be moving because they're in orbit around the center of the Milky Way. If they weren't moving, gravity from the combined mass of the Milky Way that lies interior to the orbit of the star would draw the star towards the center of the Milky Way. Well, the center of the Milky Way and the star would come towards each other, but because the rest of the Milky Way is more massive, essentially the star is moving towards the center of mass.
Which gets into, I'm sorry, it made me think of something else. People often ask why we don't send our garbage or our nuclear waste into the sun, and are amazed when scientists like myself tell them that it would actually take less energy to shoot it out of the solar system. And they're like, how can that be? Well, because anything we launch off of Earth has the same momentum, the same speed as Earth. So you've got to kill all that speed for it to fall into the sun. And doing that takes more energy than just flinging it out to begin with.
Yeah, the other thing I remember, and I guess this was discussed a lot back in the 1970s, was the idea that we could take our nuclear waste. Remember, it was starting to pile up, so there's a big controversy in Arizona where to put the waste. They wanted to put it underground in a certain location, and people rose up against that idea. I haven't really heard much about that lately, so I don't know what's going on. I think they're just storing it outside the individual nuclear power plants.
That's pretty much it, yeah.
So the idea was to take the nuclear waste, put it on board a rocket, send it into space, and send it into the sun, and then you'd be rid of it.
Right.
But then if you send up, I don't know how many rockets, let's say 100 rockets, and the way, if you look back on the history of rocketry, a few in 100 will explode. So you have this rocket exploding, let's say half a mile off the launch pad, and all that nuclear waste is going everywhere. Yep. You're polluting the Earth environment, of course. Other people argued that no, we can build container explosive or proof containers that this nuclear waste could be in. So even if the rocket did destruct, right, it did blow up, then partly up up into the going up in the atmosphere, that radioactive material will not get spread around the Earth, so you wouldn't
Right.
damage the environment. But you just need that to not to work once and you're messed up, right? Because
Right.
you'd have all of that stuff released into the upper
And-
air
and
atmosphere.
I've seen the tests of these containment facilities. We're getting way off topic, but it's still a relevant and good topic. I've seen the test, the containers they put the waste in. I've watched where they ran a train into it, and they had to repaint it.
Right.
Okay,
Yeah.
they ran a train into it. It's kind of like the reactor. I watched where they flew an F-4 Phantom, had it on rails and just set the engine to go. By the way, didn't have a pilot in it. Anyway, they flew it into the concrete that the reactors are housed in, and yeah, it crumpled the F-4 Phantom, and the concrete looked like, something happened.
Yeah, the problem with all of that, and that's fine and dandy,
Yeah.
right? But if you ever got to a situation where humans obviously make mistakes,
Right.
so this thing needs to be 100% reliable, or you're in big trouble. You just have to mess up once, and you're done.
And you want to talk about where AI could come
Right.
in, because it can monitor a heck of a lot and react a whole lot faster than a human can.
This issue was a big deal a few years back. I remember during the preparation for the launch of the Cassini mission to Saturn. So that was a mission that went in orbit around Saturn, and it had a probe that parachuted on Huygens probe that landed on Titan,
Yep.
built by the European Space Agency. There is essentially a nuclear material, plutonium, that's on board Cassini, and they use these radioisotope thermoelectric generators that basically you have a lump of plutonium that decays, and as it decays, it releases heat, and that heat gets transferred into energy, and it's that energy that powers the spacecraft. And the
Right.
reason why NASA did this is because Saturn is so far away from the sun that you would need such a large solar panels to generate solar power to run all these instruments. It was impractical at the time.
So,
Okay.
in other words, what you're saying is even at Saturn, the sun has become more of a star.
Yeah, that's right. It's so weak
We've
in
come
terms,
around circle.
right. It's so weak in terms of its brightness. It's hard to get anything out of it in terms of solar energy. But of course, we can build better solar panels that are more efficient. We can even advance the material technology so we can make solar panels thinner, so we can make them larger in area when they fold out.
Right.
And we can even develop heavier lift rockets. I'm thinking of the SLS and so on. That maybe you could get a larger set of solar panels to Saturn that's practical.
Without needing an RTB, because I'm going to point out we need those isotopes to make medical isotopes here on Earth.
Right, the
We
plutonium.
don't need to be sending it off into space for that reason, if nothing else.
And the controversy at the time is when the Cassini mission was being launched, people were protesting and actually at the launch pad down at the Kennedy Space Center trying to stop the launch from happening, because if there was a failure during the launch, there was worry that plutonium would be spread through the upper atmosphere,
Right.
would be vaporized, and it would be in the most dangerous form ever possible, for human life, right? You've been breathing this stuff
You're breathing it in. Yeah.
But that went away, and NASA showed that no, the chance of this happening is so small. It's the risk is manageable, not to worry about it, and so the launch went ahead.
Right.
But people are thinking about these things, and once again, it ties into the fact it's a use of our own sun.
Right.
Right now, there's been news lately about
Okay.
our sun, which is kind of interesting. And this is the slide that you're seeing here is sort of a copy of the front page of the paper that was just submitted for publication recently. And this paper describes activity on sun-like stars. Now, why this is interesting is that one of the things that we tried to understand in astronomy is the properties or the long-term evolution, let's say, of individual objects by looking at collections or ensemble of objects. For example, let's say you wanted to understand how trees grow. So you walk into a forest. Now, let's say a typical tree takes about 200 years to go from from a seedling all the way up until it's full grown. It lives its life, and then finally it falls over and decays. Now, if you want to understand everything about a tree, its whole life cycle from the beginning to the end, are you going to be able to hang around in a forest for 200 years and piece all that information together?
Yes.
Right. I wish we could, but
Absolutely.
unfortunately, the average lifespan of a human being is roughly 80 years.
It's roughly
Okay? Depending,
1/4
of
the
course,
length of the
where
tree.
yeah, depending on where you live, of course, in the world and so on and so forth. But no, we can't do that. So what do we do instead? Well, we can look at collections of trees. So we go into a forest that may contain hundreds to thousands of trees, and by looking around, we can see maybe trees that are just growing today, little seedlings that are coming up from the forest floor. We can look at trees that have, that are a year old. We can look at trees that are 50 years old and so on. And we can even look at trees that have recently fallen on the forest floor. They're at the end of their lives, they decayed. Maybe they got pushed over by wind because they become very weak in their late ages and these kind of things. And by piecing all that information together of all a collection of trees, we can understand the whole process of the evolution cycle of a tree.
Right.
Now, we do the same thing then for stars. We can look at collections of stars, so thousands of stars that are similar to our own sun. Some of these stars will be in the early part of their lives. Some of these stars maybe are at the end points of their lives, and of course some will be in between, middle-aged type of stars. Now, we know from dating rocks here on the Earth and on the Moon and the meteorites and so on, that the age of the Earth is a little over 4.5 billion years, correct?
Right. Correct.
Okay, and so we infer that our sun and also the other objects in our solar system all formed at approximately the same time.
Which is that seems a reasonable assumption to me. Yeah.
Which means we have a direct method, well, sort of direct, of dating the sun itself.
Right.
Right? So the sun
And
can
we
be...
have other indirect methods as well, but
Yeah.
we'll get into that another show.
So we can peg the sun at about 4.5 billion years old. Now, if you see another star out in space, how do you determine the age of that star, even if it's the same type of star like our own sun?
Okay. Which I was about to say, which type? Because
Yeah, a G2.
that makes it a G2.
A G2 type
would I age
spectral
a
type.
G2?
How do you age it? You can't.
You can't really because it's not convective throughout, so the ratio of hydrogen to helium won't help you.
No, you can't tell.
You can't tell.
So that's what I mean. We're in this prime situation where we can date our own sun, but when you look at an isolated star, you can't date it. It doesn't even have to be a star like our sun. You can't date it.
Right.
That's why looking at collection of stars, and I don't mean just stars randomly selected all over the sky that are part of our Milky Way, but we look at collection of stars where stars are close together in star clusters.
Right.
And by looking and analyzing star clusters, we make the assumption that all stars in that very specific cluster, let's say, formed at the same time. Mm-hmm. So we can look at the properties of all those different types of stars and note, for example, which is the most massive star that's still on the main sequence. And by knowing what type of star that is, so its turn next, if you like, to evolve off the main sequence, we can date those stars from our physical models that we put together.
Wonder Goon, yeah. We could tell you, but we'd have to shoot you. No, there's just some topics that, we'll come up with another show, and dating the age of the sun is one of those topics because there are other ways to get at that age.
Exactly. And so the other thing too to note here then is if you want to understand about the full life cycle of a particular star, like our sun, and stars, how they evolve depends on the primary property is their mass, right?
Right.
So we look at stars that are essentially a solar mass, solar-like stars. And that can tell us a lot about what happens in the lifetime of these stars, assuming you look at a large population that you're going to catch just by random chance stars at various parts of their life cycle, correct?
Correct.
Okay. So putting all that together, this study that we're showing here is interesting. Why? Because the authors of this study looked at stars that are similar to our own sun. The data comes from the Kepler telescope, space telescope that NASA put up several years ago. It's no longer functioning. Its primary role was to look for exoplanets, the transiting method, which means imagine a planet passes in front of a star relative to us. That causes the brightness of the star to dim for a period of time. And then when that star gets out of the way, if you like, then it brightens back up again. And we can watch or look at these periodic dimming in the brightness of stars to infer the type of planets that are orbiting that particular star. So that was the primary function of the Kepler data. But because the Kepler data measured very precisely the brightness of stars, and therefore any change that may occur in those brightness of stars, they could tell if a particular star may have brightened slightly for a period of time due to the fact there was a solar flare type event happening on the star.
I never thought about that use for Kepler.
So what you
Yeah.
can do is go through the database of all of these observations that have been accumulated and recorded and available to the public. It's not something you need a special key to get at, right?
You might need some special training to be able to interpret the data.
Well,
but-
sure. So then they have done in this study, the authors, is they looked at these solar type stars, and what they discovered was that some fraction of them have once in a while what we call these super flares. So what are these super flares? Robert, do you want to describe what a flare is on the sun and something more about it?
A flare on the sun is simply an active region where the sun gets really, really hot for a short time. Short maybe up to a few hours. And so if you're looking at the sun at the time, what a flare looks like is just a bright spot on the sun. But these bright spots are where the solar wind comes from, a phenomena we call a coronal mass ejection comes from, and they are also usually associated with sunspots. So you've got all these nice correlations and connotations, but some flares are not associated with sunspots. Some do not produce coronal mass ejection. Some, you get the idea.
Now, so Robert, if you had a very, very energetic flare that goes off, and that's the term they're giving here, super flares. It's not just a standard solar flare that we'd see, usually during when the sun reaches its maximum activity, which we're getting into nowadays, right? And we don't know exactly when the maximum will occur. Some people suggest next year or the year after, but we're ramping up. The solar activity is ramping up. We can see that by increasing the number of sunspots that we've seen over the last year or so. And so one of these super flares can be so energetic. What could that possibly do if it was pointed in the right way and the Earth was in the right spot at the wrong time? Put it that way.
Well, I will refer to an event that happened in the 1800s called the Carrington event. And one of the neat things that happened is that the aurora borealis, were seen as far south as Havana, Cuba. So that's kind of neat. But it also caused telegraphs to catch on fire because part of the emission from those flares is radio waves. And what long wires stretched across the countryside act as is an antenna to absorb that radio energy. And so the telegraph wires were collecting this solar flare energy and directing it into the telegraphs, and they were pretty much exploding in a few cases.
Now, this is in a time before the telephone was invented.
This is before the telephone. This is before the international, essentially, power grid that we now have.
Right.
So if this type of event happened now, we'd be in some serious trouble.
Well, wasn't it just a couple decades ago that up in the province of Quebec in Canada, there was solar activity that caused a surge in the power lines that caused major blackouts.
Yes, I remember that.
Yeah. So, there has been problems in the past. And the difficulty in all of this is you can't predict what happens to our sun. And that's why this study is important. If you can't live long enough to monitor the activity and even predict when something would happen, what you can do is go to other stars that are like our sun and see how they are behaving.
And see how frequent they are.
Right, and we see that there are times when these sun-like stars misbehave and create these super flares.
Now they get cranky.
Well, these super flares can be so energetic, and this is even more so than the event that happened, the Carrington event in the 1800s. They can be so energetic that when that radiation, those high-energy particles, bombards our upper atmosphere, they can energize that atmosphere to essentially boil it off.
Boil it off.
There goes the atmosphere of the Earth.
Right.
Game over.
Game over.
Now, so then at this point, we're saying, what we'd like to ask the question that how probable is that? Well, we don't know. We know it hasn't happened in a long period of time. You can look at historical records and do core sampling and look at fossil records and so on to get an idea if there's been any kind of high event like this, a radiation event. But we see this type of activity happening on sun-like stars. That's why this paper is extremely important. Yeah. So we know it's not out of the realm of possibility that someday our sun could release a super flare that essentially strips away the Earth's atmosphere.
Right.
Now, is it probable? No. But the probability is not zero. Sorry, folks.
Yeah.
It could happen.
Say this as a joke, but it's not really a joke. The universe really is out to kill us. Okay? It's that simple. There are so many things that could happen that just wipe out all life on Earth. Is any one of them likely? No. Together? You got to wonder.
Well, has there been mass extinctions on the Earth?
I don't know. Oh, yeah, there have.
Well, what
There you
caused those?
Right. A few have been, we've traced to asteroidal impacts. A few we've traced to, we don't know, sudden changes in Earth's atmosphere. Could it have been a super flare? Absolutely.
When you think of volcanic
Or
activity,
volcanic activity.
there's all kinds of possibilities. There's lots of ways to die,
That's it.
unfortunately.
Unfortunately, yeah.
So, but when you go to, and it's kind of unusual when you think about this, like, it's like, oh, the sun doesn't appear to be active. In fact, if you go out during the day and you look up at the sun, you see this sort of yellow ball in the sky. By the way, that yellow light is due to the fact that the sunlight passes through the Earth's atmosphere, and a lot of the shortwave length optical light gets scattered out from the line of sight. That gives rise to the blue sky that we see on a clear day.
You put that blue back into the yellow sun, and guess which color you get?
Yeah, so when you're
White.
so you can if you ever run across an astronaut and you ask them what is the color of the sun when they're in space and they look up at the sun through the window of the International Space Station, whatever, they'll say it's white. It's not yellow. So the yellow effect is due to the Earth's atmosphere. But anyways, when you look up at the sun, you see this sort of homogeneous, bland type of object. It looks like you can't see anything on the surface of the sun at all. And you might think that, it doesn't look dynamic to me. There's nothing weird going on. But of course, if you have a telescope, and this is an image taken with the Solar Dynamics Observatory of NASA's spacecraft we have in space, looking at the sun, this is an image that was taken yesterday. And what you see is the sun is not completely bland or uniform in color. There are spots on the surface of the sun. These are the so-called sunspots. These are magnetic storms on the surface of the sun. And by the way, that part of the sun that you can see with your eye, that's known as the photosphere. There are other layers of the sun that we have that you can't see in the optical. For example, the chromosphere is observable in the ultraviolet. And the one that you see during a total solar eclipse is known as the corona.
And that's visible in X-ray.
That's visible X-ray, but it's also visible in optical light. It's just that optical light is so dim, the photosphere overwhelms it. It's like looking at a firefly that's perched on the edge of a searchlight that's beaming at you. You can't see the firefly. It's overwhelmed by the searchlight. But when the photosphere of the sun is blocked by the moon during a total solar eclipse, then we can see that fainter light coming from the corona. And so there's eclipse coming up on April the 8th next year.
Woo!
So that path of totality passes through the United States and up into eastern Canada. So this is a heads up to get ready for that event. So if you Google the path of totality for the April 8th, 2024 solar eclipse, then that'll give you information where you need to be to see a total solar eclipse of the sun. And during that total solar eclipse, at that point where the photosphere of the sun is completely blocked by our moon, then you can see the corona. You don't need binoculars, you don't need telescopes. You can see dramatically then with your own unaided eyes.
And I'm going to bring up a point. At totality, folks, you can look towards the sun with your unaided eye, with just your blank eye. Don't look for very long, though, because as soon as the moon moves out of the way, we're back to you can blind yourself. But at that time of totality, which usually lasts about a minute to 2 minutes at least,
Right.
you can look safely at the sun.
Yeah, so the rule of thumb here is never, ever, ever, ever look at the sun directly with the unaided eye and stare at the sun.
So how do we get telescope images like this?
Right, so what we do is we can filter them, right? So there are processes, there are ways that we can reduce the amount of light then that we're getting from the sun. So Robert, do you want to describe this a little bit?
So this is one of the ways, and this is called an etalon. And an etalon is essentially two semi-mirrored pieces of glass that are polished to be very flat. And what happens is it acts as a resonance cavity that traps light and reflects all of it out except a very narrow band of very narrow set of wavelengths. And you can tune that by changing the spacing between the two plates. And so this is what's used to produce what's called an H alpha telescope that looks at that, you've mentioned it before, that red hydrogen line. And so this allows us to see a lot of details about the chromosphere, which is got a lot of ionized hydrogen in it, and the photosphere, which also has a lot of ionized hydrogen. But this is one of the ways we do it. Another way we do it is just put a partially silvered piece of glass in the way. Don't let that get into the light, get into the telescope in the first place. Just allow a small fraction, like 0.001%, to get through, period. And either of these methods, the etalon or the partial mirroring, will do that effect. But again, Galileo made himself blind a few times looking at the sun before he figured out how to properly filter it. Don't look at the sun unless you've got a reputable source for a telescope that is dedicated to looking at the sun.
Yeah, you have to be extremely careful. I know there's been things made in the past for amateur type telescopes that are not great design.
Right.
And there have been problems that people have damaged their eyesight using this type of equipment. So you got to really know what you're doing. So please, unless you know what you're doing, do not look at the sun through a telescope or binoculars or any other optical device. Do not ever do that.
When in doubt, consult a professional. Consult somebody who knows what they're doing. I have a few sites that I could recommend, but we won't get into that because I'll be advertising for someone. But,
well, there's even solar eclipse glasses that one could use to look at the sun during a solar eclipse. And if you happen to obtain one of these for the eclipse coming up next year, the other thing is take very good care of them. Don't scratch them. Don't damage them in any way, because any type of damage that can allow the light to pass through that and not be filtered properly will also, once again, can cause permanent damage to your eyes.
And I will add, because I have gotten a pair of the not good ones, and I've looked very briefly at the sun. I will tell you, you will know when these things aren't good for looking at the sun. Your eyes will feel hot. They'll start to hurt. Don't do it. Look away immediately if you feel any of those types of sensations, because it may look dark, but the infrared may be getting through.
Yeah, it's not worth taking the chance and losing your eyesight.
Right.
To look at the sun during eclipse.
But the biggest thing I can say is buy these such things from reputable dealers, people who know what they're doing, who are established solar telescope type people.
Right. So, Robert, if you want to go
back up.
Yeah. If you go to number 2, actually.
So that one.
Yeah, so getting back to the point that the sun itself then can be dynamic, right? There are storms on the surface of the sun, even though you just can't see them with the unaided eye. When you have the proper equipment, then you can see this type of stuff. So this is an image then of the sun that you're seeing here, looking at a burst of particles that is being emitted from our sun. If you watch this, it's just a looping clip of the sun itself, you can see that burst of particles coming off sort of to the lower right in this movie clip that you're seeing here. So this is a proper filtered space-based telescope that looking at very short wavelength of the light coming from the sun itself. And the thing to get here is the sun is very dynamic. It's very, very active. It's bubbling, it's boiling, the surface like convection, like a pot of water that's boiling on your stove. There's things changing and happening all the time in real time.
Yep.
And so the sun is not this bland, unchanging, yellow disk that's featureless that you see in the sky. That is not what's happening with the sun.
And I will note there are, at one point or another, there are 4 flares on the sun right now. People often think that those things that look like flame are flares. No, those bright spots you can see, those are flares. And I'm talking about the ones that look white, the really bright spots.
Yeah.
That's all a flare will look like, is a really bright spot on the sun.
And in this burst of particles you see coming off the sun, you can see that associated with one of those bright white areas, right?
Right.
So these are these areas where you get released of what they call coronal mass ejection. You get charged particles that are being released then from certain areas of the sun's surface itself. Now, if it happens that those particles reach the Earth, that can cause, aurora activity. So we could have a display of northern lights for a night or two, and also southern lights, of course.
We can also lose satellites. That's satellite communication.
That's the other thing, is that we have a lot of very sensitive technology that's in orbit around the Earth that we rely on, like whether it's internet access, communications, so even military satellites, that there can be a burst of solar activity that causes these charged particles to hit the upper atmosphere of the Earth and even damage these satellites, short circuit them. And so you can imagine that if one of these super flares did occur on the Earth, it wasn't enough to strip away our atmosphere. It could do significant damage to all of the satellites in Earth orbit. Now, there are approximately, roughly 9,000 satellites in Earth orbit. Not all of them are active, of course. But you imagine that all of them get destroyed. All the electronics get fried, essentially, of every single satellite that's in Earth orbit. What would life be like in the country that we live in now, in Western society?
Let's see, forget your streaming services because there's no internet. Forget finding your way around unless you are old like me and know how to use a map because GPS just went out. It's not a pleasant place to think about it. For a few days, I guarantee you've lost your cell phone coverage because it'll knock out the microwave towers. And it may very well, depending on how fast their system react to the surge in power, it may do like in Canada and knock out the entire power grid.
Now, I worry about two things. First of all, the long term. How long would it take us to reconstruct that network?
Considering there are about 5, if I remember correctly, substations built and ready to go to replace blown out ones, it's estimated it would take 30 years for us to recover from something like that.
Short term, if the event occurred and if it, let's say at 1 p.m. tomorrow afternoon, if it happens, it's a total coincidence. It's nothing that we did or said during this podcast, right? There's our disclaimer. By the way, the opinions of Robert and I are our own personal opinions and not necessarily opinions of the university or anyone else associated with the university.
Right.
Now, let's say it happened at 1 p.m. tomorrow afternoon, our time, right? Mm-hmm. Central Daylight Time. How do you know that wasn't a nuclear attack by an enemy of the United States?
Because it would be global.
You see what I'm saying?
Right. No, I get
Is
what you're
there a
saying.
risk of misinterpreting the event?
Absolutely, there's a risk. Yeah.
And that would mean that we would have launch full-scale retaliatory strikes immediately.
Yep.
So that could be the end of Earth, civilization as we know it today.
Yep.
Just because of something that happened on the sun that we could normally then have recovered from. In fact, if you go back to the early 1800s when we didn't even have a telegraph system, if an event like that happened on the sun, there's obviously no satellites. They were launched, the first one in 1957, I think it was.
Yeah,
right?
Sputnik.
The Sputnik. So, and there's no telegraph system to worry about. So the only thing we would know would be dramatic northern and southern lights, aurora activity for maybe a few nights or whatever. But that would be it. It would have no impact on day-to-day life on the surface of the Earth.
Right.
Where if it happens today, it could be the end of civilization.
Absolutely. So how do we prepare for that?
So,
well,
Robert, from a philosophical point of view, Robert, do we live in a better time today or 200 years ago?
I say we live better today, but I have medical conditions that I wouldn't have survived 200 years ago. So I say we live in a better time today. Do we live in a more vulnerable? Yes, there are more places where kinks in the system allow for glitches. But we're working on getting it where those glitches can't happen. So.
Now, Robert, you have an illustration of a dramatic event that occurred on the sun as well.
The CME, the coronal mass ejection you're seeing in this video, is aimed at us because it's coming at us, right? Mm-hmm. Here's what we've dodged a few times going off the side of the sun. Now, this is a masked, a coronagraphed image of the sun. The white circle in the middle represents where the sun actually is, and they put a big disc so that they can see the corona better. And you can see what a really big coronal mass ejection looks like, and we got 2 of them blowing off on opposite sides of the sun. Fortunately, these were not aimed at us. Otherwise, we'd just see a bright flash and everything. But this is what a big one looks like.
Right, so this looks like an image taken from the SOHO spacecraft.
This was probably almost certainly SOHO. Yes.
And the circle you're seeing, that's the actual apparent size of the sun from the distance of the SOHO spacecraft.
Right.
So it gives you a perspective of how large the sun would be. Then it's just that it's so bright you would swamp the detector.
Yep.
And you can see then the sun is not, dull, and that there's lots of stuff that goes on associated with our sun, lots of activity.
And other things I'll point out is yes, you've got this mighty impressive coronal mass ejection, CME, going on. But if you notice, people always go, where are the stars? Well, you'd see little white bright flecks in the background through the corona. Those are stars. You've got one streak, which is what we call a sun-grazing comet that was in the frame. And you can also see the coronal material looks like it's in strands, in wisps. Well, that's because it's ionized, so it lines up along the sun's magnetic field. So even the coronal mass ejection looks like it's following these magnetic fields, and that's because that's exactly what it's doing. And one of the things that creates these coronal mass ejections is that you get what's called reconnection, magnetic reconnection, where a north pole and a south pole actually come together, and that releases a lot of energy when that happens and blows some material off. And so that's what causes some of these CMEs.
Yeah, in fact, there's been a great mystery, and we have talked about this in a previous podcast, about if you actually look at the temperature of the different layers of the sun, and you can do that by looking at the sun's spectrum and looking at the ionization state of the various elements in the atmosphere of the sun. For example, if you see iron and it has, let's say, multiple electrons stripped away from the iron atoms, it takes a certain amount of temperature to do that, certain amount of energy, which correlates to temperature. So when we look at the corona, that part of the outer atmosphere of the sun that we see during a total solar eclipse, we determine by looking at the spectrum of the light coming from the corona that corona is literally tens of millions of degrees. It is extremely hot. And yet it's the furthest in terms of the atmosphere of the sun away from the center of the sun, where the energy, that power plant of the sun resides. That's the nuclear fusion of hydrogen and helium. So the great mystery over many decades now had been what heats the corona.
Right.
And it's a lot of the stuff that you mentioned.
A lot of that magnetic reconnections and so forth that's doing it. Now, people go, how can it be that hot? How can it be hotter than the surface of the sun? How do we know it's that hot? Well, the thing you got to remember is you could freeze to death in the corona of the sun. What? The corona is a better vacuum than anything we've ever produced on Earth's surface. Okay? So we've sucked out to where we can count the atoms in the vacuum boxes that we've made here on Earth. And the corona is more of a vacuum than that. So while we can see it and it looks, that's because it's hot and it's glowing. But there's actually very little material in any given volume in that region of the space. So it looks pretty and it looks like there's a lot there, but it's really because it's so big and so hot.
Yeah, and
so,
I can do an analogy with that if you want. So imagine you're standing on the surface of a planet.
Mm-hmm.
You have your spacesuit on. It's a near vacuum. It has just a little bit of wisp of an atmosphere. And we determine that the winds on the surface of this planet, it exceeds 600 miles per hour.
Oh, right. Yeah.
Now you wonder, there's no way I can stand on that. That's way more than an EF5 tornado by far. So how am I going to stand on the surface of the planet when the winds are blowing at 600 miles per hour? Well, if it's a near vacuum, there are relatively very few atmospheric gas particles per cubic meter of space that are hitting you. And what we really want to know is what is the force per unit area. In other words, the pressure of the atmosphere on you. And in this case, the force is so small because you have so few gas molecules that are impacting you that the pressure is so little that you can't breathe. You need a spacesuit. It's a near vacuum environment.
Right.
So the wind traveling at 600 miles per hour is not going to do anything to you at all. It's not going to push you over or something like that.
Right.
So it's analogous to
It's kind of the same situation.
Yeah.
It's like we estimate that the winds on the surface of Venus are only about 2 to 3 miles per hour. But Venus's atmosphere is so much thicker than Earth that 2 to 3 mile an hour winds will knock you down.
Right. I mean, it's the density that really matters here, right? It's the density.
It's that pressure. That's a very good way of putting it. There's almost no pressure in the corona, but there's high temperature.
Yes.
So, means particles are moving really fast, but there's very few of them.
Yeah, and then the way we probe the temperature, as I mentioned, is we look at the spectral lines.
Right.
So the way that we understand how atoms work, right? It takes a certain amount of energy to strip one or more electrons, let's say off of hydrogen. Hydrogen is the most abundant ordinary matter that's out there in the universe.
Yep.
And I have to make that distinction because what dominates in terms of matter is dark matter, something we also referred to in the previous podcast. But we're talking about ordinary matter, matter that you'd see on the periodic table, if you remember back in your high school days.
Right.
So hydrogen is by far the most abundant element. So if you just concentrate on the hydrogen atom, then electrons are stripped away from the hydrogen, then that's in the outer atmosphere of the sun. Well, what temperature do you need then to create particles that have enough speed that they can literally strip away the electron from hydrogen atoms? It's on the order of about 10,000 Kelvin. So
Right.
let's say about 10,000 degrees. Don't worry about the conversion from Kelvins to Fahrenheit or to Celsius. It's
Because
roughly
it
the
doesn't
same.
matter at
It's
that
roughly the
temperature.
same at that temperature. But if you go then to look at other species of atoms, like iron, for example, as I mentioned before, and you see one or more electrons stripped off an iron atom, what temperature would be required? In other words, what energy is required to do that?
And it's real neat because to strip off the first electron from iron is less energy than to strip the one electron off of hydrogen. But to get that second electron takes a lot of energy. To get that third takes even more.
And then fourth, because we see, multiple ionized states of iron, for example. They've
Right.
lost several electrons per iron atom on average.
And so to get iron to lose 4 electrons takes temperatures of 1,000,000 degrees and more.
Yeah, so by looking at these different types of atoms and their what we call their ionization states, it's a very, very delicate, diagnostic probe to what the temperature of that gas is. And that's how we come up with these values, the numbers of being,
Right.
10 million degrees in terms of their temperature.
It's not that we've flown a thermometer up there and stuck it in the sun.
That's right.
It's that we've looked at these ionization states and go, to do that ionization level, requires this amount of energy, which translates to this temperature.
And of course, if you needed to go to the sun and stick a thermometer in it to measure its temperature, I suggest we'll just send a graduate student to do that.
Absolutely.
Just kidding.
We got plenty of grad students. Come on.
Well, when I was in graduate school, that was always and that's been like that for many years.
Yeah.
If it's something hard and difficult, you get the graduate student to do it, right?
Right,
Not
right.
the professor type of thing.
And if the grad student isn't able to pull it off, then you talk to a postdoc.
Right. Okay, did you have anything else you wanted to talk about?
I have one
Something
last
else?
slide to talk
Yeah.
about. If you're more interested in learning about the sun or just looking at neat pictures of the sun, here are 3 websites that exhibit very good information. One is we've shown you some of the pictures from. It's SDO, Solar Dynamic Observatory. It's in space. It's mainly looking at X-ray and hard ultraviolet.
Which means short wavelength.
Short wavelength.
When you say higher.
So that's why we've got to have it in space, actually, is because the atmosphere will block X-rays and hard UV.
And what in our atmosphere blocks the ultraviolet?
That would be the ozone.
The ozone layer.
The
And that's
O3
why,
layer.
we've heard a lot about pollution and destroying our ozone, right, in the upper atmosphere from the CFC chemicals that were released. This really got going, I think, in the 70s,
Yeah.
right? And we try to cut back on the use of those chemicals because if you destroy the ozone layer, what happens to you if you're laying out in the beach in the summertime?
Zorch.
Yeah, so you'll get a real nasty sunburn. In fact, if you destroy the ozone layer, that's not good for life here on Earth.
And we're such negative Nellies sometimes that I've got to say and point out that the laws and regulations that were enacted have actually worked. The ozone layer is actually repairing itself now.
Right.
So, people can say, oh, we can't do anything about these changes. Yeah, we really can. So keep that in mind. Just
Well,
going to throw that out there.
It's another example, whether you believe it or not. It's no belief involved. It's not a belief system. It's science. Science is
Right.
not a belief system. If you come up with ideas, you test them. If the tests show your ideas are wrong, you move on to something else. There's no belief. Doesn't matter if you believe in it or not, right? You go by
Right.
what the evidence shows. And what we know is, and we've done it, we have made changes to the global environment of the Earth. I'm sorry, but that is the case.
That is the case.
One example is we've destroyed some of the ozone layer, and we had to be careful because we need that. Life evolved on this planet, at least recently, with an ozone layer.
Yep.
And so that can destroy a lot of life forms if all of a sudden the surface of the Earth is bombarded by the full ultraviolet output that we receive, at 1 astronomical unit distance from the sun itself, where we are here in our orbit around the sun on the Earth.
Yeah. It essentially sterilized down to bacteria.
Right, and that's why we worry about things like going to Mars. What kind of damage has the ultraviolet light from the sun done on the surface of Mars itself?
Right.
So the idea is, well, maybe it would cause sterilization of the surface, but let's dig underneath the soil a little bit because the soil acts like a shield. Well, here on Earth, it's the ozone layer that acts like a shield that blocks the ultraviolet in the X-rays.
Absolutely.
And I always joke and say, if you can afford to build yourself an X-ray telescope and you put it in your backyard, and you want to study astronomical sources, it's completely useless. Why? Because the X-rays don't penetrate down to the surface of the Earth. They get blocked by our atmosphere. You've got to put your X-ray telescope in space.
There you go. So the other two sites, spaceweather.com, wonderful site. They count solar sunspots. They keep track of solar activity. They predict geomagnetic storms due to the coronal mass ejections. They give predictions about aurora. And they look at near-Earth asteroids. So a lot of good information at spaceweather.com. And then finally, there's NSO, the National Solar Observatory. It's good for looking at H-alpha images, which show a lot of the prominences, the flames on the side of the sun, a lot of the stuff we associate with pictures of the sun. They also do some good science with what are called magnetograms, which look at the magnetic field of the sun. And so very good sites. I highly recommend checking them out if you're interested in looking at information about the sun and near-Earth objects and things like that.
In fact, you can go to these sites if you like and get essentially almost a real-time view of what our sun looks like at various wavelengths.
Right.
Not just the optical that we can see, but in the ultraviolet, X-ray, and those kind of things. So it's a good resource. And with the internet, of course, there's information about all kinds of stuff.
Right. They're good sites. They really are. SDO and NSO, I know for a fact, are running real-time current images of the sun.
Yeah,
So,
and in fact, we started this whole discussion today looking at a paper that was looking at solar flares from the Kepler spacecraft. But there are other data available that one can do this.
Mm-hmm.
So I'm thinking in particular of the Gaia mission.
Oh yeah, Gaia.
So Gaia has been, measuring the photometry of stars very, very accurately. Mm-hmm. And so if one could go in their database and look at information about solar type stars, right, as long as you have matching spectra, and so one could actually analyze that data stream.
Absolutely.
And see if they detect, any type of solar flare like phenomena from those objects.
And I mentioned that you need some specialized training. This is not difficult training. You don't have to do calculus to work with this data. You just have to learn what these columns of numbers mean, and then be able to use some means of manipulating those numbers to see the patterns of when they get larger and when they get smaller, and such as that. So.
Yeah, in fact, if you want to learn calculus and you want to learn in more detail about these type of analysis, you can think about coming here, for example.
Yeah, absolutely. Right? Join us. Come on.
We have a program in physics and astrophysics, and a lot of the science type of analysis that one does, it's applicable to different areas in science. It's not just applicable to astrophysics or astronomy. It can be different types of physics and different types of biology, humanities, social sciences. There's all kinds of places where you can use math in terms of looking for correlation, doing detailed analysis, making plots, looking for trends, looking for correlations and these kind of things, and trying to understand why certain things are the way they are.
And this is why I will also recommend and have recommended to our science majors, take some of the humanities, take some of the social sciences, because it will offer you a different perspective on your science to take these classes. And this is why we have a core curriculum. And here I am tooting the horn for the idea of this broad breadth of knowledge. It helps.
So you could be under the starry skies of northern Scotland or the great state of Georgia and still take classes from us.
Absolutely.
Through the online type of situation that we're involved in nowadays. So it's a great thing when you think about it.
I agree. And, I'm sitting here going, come join us. I'm saying come join us at the university. Come by and see me and talk to me, though. I can give you a few pointers and talk with you about just about anything. So.
And the other thing is you don't need to get a commitment, a 4-year commitment into doing a bachelor's degree at the university if you don't want to. You can just take one class, something that you're interested in, sort of a continuous education type of situation. Right. And so if you're interested in a very specific class, whether it's first-year geology or maybe it's first year introductory astronomy or something like that, you can take those type of classes online, and that would greatly expand, maybe your interest, and maybe you become interested in something and you decided to take a bachelor's program in something.
Right.
Who knows?
Who knows? Right. And yeah, it's great stuff. We'd love to have you. We love to have your questions. So come talk to us. Come consider UND.
Now, the other thing that you could think of too is when we talk about the sun, we can stay with the sun, I guess, because we're almost done the podcast anyway.
Right.
So let's just stay with the sun.
Okay.
And
Yeah.
talk about other stuff next time. One of the things that's interesting when we look at the sun is the fact that it's in a state of evolution constantly.
Yes.
And do you realize, Robert, that not that long ago, and okay, it's relatively speaking, but I'm thinking in terms of the lifetime of the Earth, 4.5 billion years, let's say about 2 billion years ago, roughly, that the sun was, several tens of percent fainter than what it is today.
Yes. Yes, it was.
So it was less luminous back then.
Mm-hmm.
So we know that over the course of time, irrespective of what we do to our environment, so let's say there was absolutely no life forms at all on the planet Earth, and it never was, okay?
Mm-hmm.
That the sun's output of energy still increases. The amount of energy that we receive from the sun will continue to increase over the whole, what we call main sequence lifetime of the sun itself, over the next roughly 6 billion years.
Well, that's because the core is contracting and getting hotter.
Yeah,
so
so
the fusion rate's going up.
So the sun is getting more luminous. In other words, its luminosity is increasing.
Mm-hmm.
What do we mean by luminosity? It's the amount of energy that's radiated per second.
Right.
Now, when you think of the stars like our sun, you think of them like balls of gas, right? And the light is emitted in all different directions. So it's not like the characteristics of light being emitted from a laser. It's not like that.
Right.
Okay, the light is uniformly emitted in all different directions. And this light spreads out an ever larger volume of space. So it's like an imaginary sphere that keeps getting larger and larger and larger, this sort of thing. And so the amount of light that you receive from the sun then, and it's just a geometric effect,
Right.
goes like 1 over the distance squared.
Absolutely.
So, for
yes.
example, if you're at a certain distance from the sun, let's use the Earth's distance, and let's say it's exactly 1 astronomical unit away,
Mm-hmm.
okay? Then the amount of light you would receive from the sun, if you doubled the distance, would be 1 over 2 squared, which is 1 over 4. So you receive 25% the amount of light that we receive at our present position. So if you double the distance, you get 1/4 the amount of light. Right. So the light falls off as 1 over distance squared. It's a purely geometric effect.
Right.
Okay. So therefore, then, as the luminosity of the sun increases, the amount of energy that gets released per second from the sun will increase over going into the future.
Mm-hmm.
So eventually it'll come to the point, several billion years from now. We don't even have to wait 6 billion years. We only have to wait, a couple billion years from now. The amount of energy we're going to receive from the sun is going to be so great, it's going to boil away all of the oceans, all of the lakes, all of the rivers. All of that is boiled away from the surface of the sun, of the earth. It's going to become a desert.
Absolutely. Yes.
And there's nothing that we did to cause that. It's the natural evolution of our sun.
But it's hundreds of millions to a billion
Billions of
from
years
now.
away. Exactly.
Okay. So this is the difference. Yeah.
So hopefully in that time,
We'll figure out a way off this rock.
we'll go somewhere else. So maybe we have to all migrate to Mars,
Right.
for example, right? We have to leave the Earth, or maybe we build cities underground and then somehow repurpose, take the vapor and condense it into liquid,
Right.
do some kind of technological innovation that helps us survive here on Earth. Who knows? There's a lot of engineering can be done in the next several 100 million years, obviously.
Right. Hopefully it won't take that long, to be honest.
But the sun is going to change. There's nothing
Yep.
we can do about it. It evolves.
Absolutely. But
Well,
I think
Robert,
we're out of time.
Yeah, so we always leave with a quote. And this quote is interesting. We think about Albert Einstein, which is what the quote comes from today. One of the things that Albert Einstein is famous for, and even in laypersons hear about this, is that God doesn't play dice with the universe. This was related to quantum mechanics, the probability effect of quantum mechanics.
Right.
And I always wondered, is that exactly what Einstein thought right up until the end? Because I know Einstein would espouse this several decades before he passed away. But is this something that Einstein would have even said, let's say in the early 1950s? So he died in 1955 of heart trouble. So would Einstein have said the same exact quote, let's say in 1950, knowing what he knew at that point about quantum mechanics, whether he followed it in detail or not? But it's interesting that John Wheeler, who also has passed away, a very famous physicist at Princeton University, where Einstein was located, he also talked to Einstein a lot, of course, a lot of communication back and forth. And he actually said that Einstein kind of altered that quote. And the altered quote is interesting. I'm going to read that quote today. So here's the quote from Einstein. Einstein said, "I still can't believe God plays dice, but maybe I have earned the right to make my mistakes."
Nice.
Now that tells me Einstein was indeed open to the possibility that quantum mechanics describes reality.
Right.
And
Didn't like it.
And that it is a probabilistic type of universe we live in, not completely deterministic.
Right.
So we're going to leave you with that quote today. Our next podcast will be 1 week's time on Tuesday, June the 20th at 3 p.m. Central Daylight Time. And so thank you for listening. Thank you for watching. Remember to give us a thumbs up. That is, like the podcast. And if you really like it, hopefully subscribe to the podcast.
Right. And if you really like it, hopefully you'll come see us.
So thank you very much.
Have a good evening.